Hey guys, welcome to the 11th video in the Math 9 SI series. Today we're going to be talking about how we can find local and absolute extrema for a given function. All right, let's go ahead then. So first off, absolute minimums and maximums. So let f be defined on some interval I, and let c be an x value in I. F of c is called the minimum if it is less than or equal to all other f of x for x within I, and f of c is called the maximum if it is greater than or equal to all other f of x for x within I. And we call these mins or maxes, we call them extreme values or extrema. So for example, we have f of x equals x squared over the closed interval -1 to 1. So here we have two absolute maxes and one absolute min. So an absolute max at x equals -1 and an absolute max at x equals 1. We can have two absolute maxes because here both of them have the same max value, which is just 1. And then our absolute min is at x equals 0 with the minimum value being 0. And notice that we treat these points as max values, and it's because we are on this closed interval. If it wasn't for this closed interval, this parabola would continue off infinitely in both directions. Okay. Next up, we have relative minimums and maximums. So again, let f be defined on some interval I, and let c be an x value in I. F of c is called a relative or local minimum if it is less than or equal to all other f of x for x in a subinterval a, b contained within I. And f of c is called a relative or local max if it is greater than or equal to all other f of x for x in a subinterval a, b contained in I. Sounds kind of complex, but all it's saying basically is that it's a relative local, or it's a relative min or max if relative to all the points directly to the left and right of it, it's like the highest point. So we'll see this in this example here, which is f of x is equal to x cubed plus 2x squared over the closed interval -2, 1. Here we have two absolute minimums, one at x equals -2 and one at x equals 0, and their max value is 0 there. And here we have a relative min, looks like somewhere between x equals -2 and -1. See that it's a relative max because all the points directly to the left and directly to the right are lower than it. But if we continue on farther to the right, we see that we are increasing past it, and we have an absolute max at x equals 1, with its max value being 3. Okay, moving on. So here's a couple of things to be careful of when we're dealing with extrema. So this first example, f of x is equal to x squared, but x cannot be equal to 0 over the open interval -infinity to infinity. Here we see we have no extrema. Why is that? Well, like I mentioned before, without having that closed interval binding us, this parabola is going to continue infinitely high. So there's no absolute max because you could pick some really high number like x equals 500. You're going to get a pretty high number for f of x there. But you could always pick a larger number and it's always going to be higher, okay? And the reason we don't have a min is because x cannot be equal to 0. Before we had an absolute min at 0, but if we have a point of discontinuity here, then we can't actually count this as a minimum, right? Reason being is that there is no definite number that is the minimum. Kind of like how we can go up infinitely. We could pick an infinitely small number, like say 0.1 is really close to 0, but it's not 0. You can say, well, maybe that's the min, but we could always pick a smaller number like 0.099 or 0.0099 or something smaller and smaller. Always go smaller in that case, so there's no minimum here. In the other example, f of x is equal to x cubed plus 2x squared, this time over the open interval -2, 1. Like before, because we have an open interval, we can't treat these as extrema because we could get infinitely close to them. And always pick a smaller number here or a larger number here. Over here, we still have the relative maximum here. It's not absolute max. It's not like because this one's not an absolute max. Now this one is the absolute max because we still have numbers that are higher than it over here. We just don't have a definite absolute max. And this one remains being the absolute minimum at x equals 0. Next up, the extreme value theorem. So the extreme value theorem says, if f is a continuous function defined on a closed interval I, then f must have both an absolute maximum and an absolute minimum on I. So it kind of makes sense intuitively. If it's continuous, that means we won't have any of those discontinuities, like those holes that were messing us up before. And if it's closed, now we know we're not going to be increasing to infinity or negative infinity everywhere. And I chose to pick a couple like simple examples here to show that even in examples that you might not think right away would have maxes and mins, they still do. So here we have f of x is equal to x over closed interval -1 to 1. So if we didn't have that closed interval, this would be just a line going infinitely high and infinitely low. But these boundaries basically give us our min here at -1 and our max here at 1. And this one is a little more weird, but f of x is equal to 1 over the closed interval -1 to 1. So this is just giving us a horizontal line. And you might not think that if it's horizontal, there's no maxes or mins, right? But if we go back to our definition of absolute maxes and mins, our only condition says it's minimum if it is less than or equal to all other f of x for x with an I, or it is greater than or equal to all other f of x for x with an I. So because they both include equal here, we're fulfilling both conditions at the same time at every point over that horizontal line. So every point on the line is both a max and a min at the same time. A little weird, but it makes sense given our definition. Next up, we have critical points. So let f be defined at C. If f prime of C is equal to 0, or if f prime of C does not exist, we call it a critical number or value of f, and we call the point C, f of C, a critical point of f. Tying this into what we've been talking about, we have Fermat's theorem. So if f of C is a local min or a local max, not an endpoint, and f prime of C exists, then f prime of C must be equal to 0. So in other words, this is basically saying a differentiable and non-endpoint max or min must be a critical point. So this kind of gives us a way of finding maxes and mins without actually knowing what the graph looks like. But do note that this does not mean the opposite. So not every critical point is a max or min. So basically every max or min is a critical point, but not every critical point is a max or a min. For some examples, we have f of x is equal to x cubed. Here we have, here we have a critical point at x equals 0, because if you take the derivative, we get f prime of x is equal to 3x squared, and we see that f prime of x equals 0 at x equals 0. So that makes it a critical point. But when we look at the actual graph of x cubed, we see that it's neither a max nor a min. It's just kind of, because of the way x cubed is built, we just kind of stop there for a little bit and then we continue. So there's points around it that are smaller than it, and there's points around it that are greater than it, so it's neither. And here is a definite algorithm that we can use to find extrema. So step 1, we want to check our endpoints, but we only want to do that if it's on a closed interval. If we're an open interval, we don't even need to worry about endpoints. Also during this step, we can check points of intersection if you're dealing with a piecewise function. So sometimes you might end up with something where like, if x is less than 1, this. If x is greater than or equal to 1, do this. And so another point you might want to check is that point x equals 1, because you have two functions that are different kind of converging at one point. So you want to see what's happening there. Step 2, we want to find all critical points. So we can do this just by taking the derivative of f and seeing every possible x where f prime of x is equal to 0 or f prime of x does not exist. After that, we want to compute the f of x for all those endpoints and critical points that we found. And then lastly, we want to compare which ones are the greatest and which ones are the smallest, and determine which are our absolute max, our absolute min, and our local max and our local min. All right. So to finish off, we're going to do this example real quick. Okay. All right. So here's our example. F of x is equal to 2x cubed plus 3x squared minus 12x plus 4. And it's going to be over the closed interval, -4 to 2. And what we're asked is to find all the extrema values. So first things first, we know that we have a closed interval, so we can just plug in our endpoints and see what we get. So that's going to be f of -4 and that's going to end up being negative 28 if you work that all out. And we have f of 2, which after working that out, we're going to get is equal to 8. So you have those, but we don't know quite what that means yet. So next we have to find our critical points, just to make sure we know exactly what's absolute max and min. So we can do that just by finding our derivative and seeing where that equals 0. Finding this is just going to be a bunch of power rule that I'm sure you're all used to by now. You get that this is going to be 6x squared plus 6x minus 12. And we want to see where this is equal to 0, right? And we can do that just by factoring. Let's pull out the 6 first, because that'll make everything look a lot nicer. Minus 2 equals 0. I don't know why I wrote a 6 there. It should just be x, right? And we want to factor this out. We see that this is just going to be 6 times x plus 2 times x minus 1 equals 0. And that is just going to be, you can see that this is just going to be x equals negative 2 and 1. And those are going to be our critical values. So with our critical values, we can go ahead and find our critical points by plugging that back into our original function f. So let's go ahead and do that. So f of negative 2 is going to come out to be 24. And f of 1 is going to come out to be negative 3. So we see finding the absolute absolute max and absolute min is pretty easy. We just need to pick out the largest and smallest out of these. We can see that this one here, 24, is our largest. So this is our max. And we see that negative 28 is our lowest. So this is our min. Now finding whether f of 2 and f of 1 are local mins or local maxes is a lot harder than finding absolute max and absolute min. In order to determine this, we're going to have to know a little bit more about the function, maybe what's happening right around f of 2 and f of 1. So you can do this a couple different ways. I'm going to do it by sketching it, because based on this function, based on these values we know and where our critical points are, we can actually go ahead and sketch a pretty nice picture. So we know f of negative 4 is our left endpoint, so we're somewhere down here at negative 28, pretty low. And our right endpoint is f of 2, which is at 8, somewhere around here. So we know critical points only are achieved when our f prime of x is 0. So we know exactly how many times this function is kind of going to turn around and like make a sudden turn. So we can use that to our advantage. So we know the next time we have one of these turnarounds, as I'll call it, is at f of negative 2 at 24. So that's our peak. So we can go ahead and sketch that. It'll look something like that. And we know it's a max, so we must be decreasing after this. So we're going to be decreasing. And the next point of interest is f of 1. So we know that it's going to be decreasing here until 1. And we know we're going to have another turnaround here because it's a critical point. And it's going to increase up until we get to our right endpoint. Okay? So factoring in what we know that this point here is our absolute max right here. So absolute max is here. Absolute min is here. So we know that this point, which is f of 1, is a local min. So that makes this a local min. And we know that this point here is going to be a local max. So this is a local max. Sorry. Okay. Hopefully you found that somewhat helpful. If you have any questions, you can leave a comment below or email me or come to office hours. All the information for that is in the description. Like usual, in the description, there's also a sign-in sheet. So if you guys could sign in, that would also help me out. New this week, though, is going to be an eval. If you could fill that out and let me know how I did this quarter, leave comments, maybe things that I can improve upon. That would really help me out a lot. So yeah, I guess that's the end of the video. I'll see you guys next week for our last video. Bye.